Hello everyone. Today we will talk about upper confidence bound or UCB in reinforced learning, and let's begin. What we are trying to solve here is a classic problem called the multi-armed bandit, and it is called that because you can think of it like standing in front of a row of slot machines or arms, and each one has a different unknown probability of giving you a reward. You don't know which one is better, and you can't try them all forever. So the challenge is, how do you decide which arm to pull over time when you don't know their true probabilities? So let's say you have got k different arms, okay, and that's just the number of choices you are working with, and over 3 rounds your job is to collect as much reward as you can. But here's the tricky part: if you always go with the one that seems good early on, you might miss out on a better option that just didn't get lucky at the start. On the other hand, if you keep exploring forever, you might waste time pulling arms that are actually worse. So we need a balance. Okay, and now the method we are focusing on is called UCB, which stands for upper confidence bounds, and it is one way to manage this trade-off between trying new options, that's exploration, and sticking with what's worked so far, which is exploitation. And UCB is not just a guess, it gives us a structured rule to follow, and it actually has theoretical guarantees that over time we won't lose too much compared to some who already knew the best arm from the start. And before we go into the formula, let me pause and ask, what is the key terminology here? First, you will hear the word regret. That's basically the difference between the reward you actually got and the best reward you could have gotten if you always knew the right action. Then there is exploration. That's when we try out actions that we are not so sure about yet, just to gather more information. Exploitation is when we go with the option that currently looks best based on what we have seen so far. And the confidence bound is here is a way expressing uncertainty. So instead of just looking at the average reward we have seen from an arm, we also add a bit extra to account for how uncertain we still are. The upper bound is this total. It is like saying this arm might not have the best average so far, but given how little we have tried it, it could still be good. Okay, and here's the formula, and let's look at this. Let me say again, just more clearly what's happening, and UCB of A equals Q of A, and that's the estimated average reward for that action, plus C times the square root of log of T divided by N of A. And here's QA is the average reward you have seen from ARM so far. C is a number you choose, usually something like the square root of 2. T is the current time step, basically the round number, and NA is how many times you have actually pulled that arm. So what is the idea behind this? Well, the first part of the formula, QA, is pretty straightforward. That's just exploitation. It says what is the average reward we have seen from this arm so far. The second part, C times the square root of log T over NA, is the exploration bonus. It gets smaller the more you have pulled that arm, and it grows slowly over time, so arms that have not been tried much get a bigger boost, which encourages the algorithm to try them, but as they get pulled more, that bonus shrinks. And algorithm details is here, 3 step. What are they? We initialize everything. For each arm A we set NA, which is the count to 0, And same with QA, the estimated reward, we start from 0 there too, and we choose the confidence value C. Okay, then in each round we choose an action. At first, if any arm has not been tried yet, that is, if NA is 0, we pull that arm. No fancy calculation, just make sure each arm gets tried at least once. Okay, after that, once all arms have some data, we calculate UCB for each one and pick the one with the highest value. Once we pull an arm and observe a reward, we update the stats. That means we increment NA and we update QA, usually with a moving average, or more generally we recalculate the average reward for that arm. And let's see what's happening in this part, and reset and start. Okay, in this simulation we have got 4 arms. You can see we adjust the number of arms, the speed of simulation, and also the confidence parameter C. Right now it is set to confidence 2 and arms 4. Okay, and each arm has a hidden reward probability. That's the true value we are trying to estimate over time. You can see the true reward values on screen, but in a real case we would not know them. Okay, and we begin pulling arms. You can see, and early on all of them might have the same observed average reward like 0, but the ones that have been tried less still have a high UCB value because of the uncertainty term. That's why you will see some arms showing infinity. Okay, and when they have not been pulled at all. And you will also notice that UCB is not deterministic in the sense that it always picks the best known average. It sometimes picks arms with lower averages because their uncertainty is high. That's the exploration at work. Now over time, as we get more data, the algorithm starts to lean more toward exploitation. The arms that consistently give better rewards will tend to get picked more often, while others get filtered out. And variations is here. One version is called UCB1 tuned. The difference here is that instead of using a fixed confidence term, it tries to adapt based on the observed variance of each arm. So if an arm has low variance, meaning the reward is pretty stable, it doesn't need as much exploration. Another version is UCBV. This one explicitly includes a variance estimate inside the formula, so it is more sensitive to arm with different reward patterns. If one arm has very spread out results, the algorithm adjusts accordingly. Okay, now where do we use this stuff? Well, one area is online advertising. You want to decide which ad to show, but you don't want to just to with what worked yesterday. User behavior might change and you need to explore new versions. UCB can help balance that out. And another example is in recommendation systems. You have got some content that's already popular, but you also want to test newer or less known options. So again, UCB gives you a way to mix what's proven with what's uncertain without going in blindly. And last thing is here, when you should use UCB, when you should not. So UCB is a solid choice if the environment is stable, that is, if the reward probabilities don't change over time. It also works best when the number of options is manageable and when you want a method that doesn't rely too much on extra tuning. But if you are dealing with a situation where things are changing frequently, like non-stationary environments, or if the action space is really huge, or if you need to use extra context or site information, then UCB might not be the best fit. In those cases, other methods might be more suitable. That's the big picture. UCB gives us a way to make decisions under uncertainty using a simple rule that balances what we have seen so far with what we have not explored enough.